It's about strain localization in metastable beta titanium alloy in relation to the beta structure. This work was done in Institut Prime in France. So we want to study beta titanium alloy with dual phases. Beta phases it's in white part and alpha phases it's dark part. We can see the different microstructure of two phases. The beta phase it's a cubic phase and the alpha phase it's hexagonal phase. It's very difficult to identify the elastic parameter and plastic parameters. So due to the different microstructure, you can see sometimes the alpha grain it's lamellar grain or equiax grain. You have the on different scale, your primary alpha grain it's dark here, secondary alpha grain here it's lamellar grain, and on beta phase you have a very small lamellar of alpha. So you have a lot of scale, so it's very difficult to identify the parameter. And you have another thing, it's orientation case. Sometimes the beta grain are one orientation and the random alpha grain it's another orientation. But due to the forging process, sometimes the alpha grain orientation, depending of beta grain orientation, you can have 12 possibility of orientation. It's just a rotation of beta grain structure, that is the Berger relationship orientation. We want to study today the effect of these two cases of orientation on the behavior of aggregate. So we have different case, lamellar case, alpha here, and equiax grain alpha, sometimes both. Grain alpha is embedded in beta grain. So we want to construct and generate a microstructure to explain the different behavior of different titanium alloy. In literature, you have a lot of different parameters for alpha grain, but it's not real different. It's around the same value of Young modulus and yield strength and tensile strength. It's due to different volume fraction and average diameter. So it's not too different. But for beta grain, you have a lot of a big difference in literature of elastic constant and different anisotropy ratio. It's a Zener anisotropy ratio. I explained that after. For the titanium alloys with beta grain. So you can see a very different value. So in this study, we want to explain and understand the behavior of dual phase microstructure. So we want to explicit modeling of hierarchy dual phase microstructure and study the strain localization. For that, we need to highlight the effect of texture of beta, the Berger orientation relationship. It's a relation on orientation of beta grain and alpha grain with 12 rotation. The volume fraction of beta, because it's really different in for different titanium alloys, and select the good set of single crystal elastic constants and study the effect of this constant. So for this study, we consider alpha grain embedded in beta grain, no laminar thickness, no laminar case, because it's difficult to generate this type of microstructure. To do that, we generate polycrystal with alpha grain. It's 2000 equiax alpha grain with in the large sample to do, because we have different scale, beta grain and alpha grain. So we need the large sample. You need enough voxel by grain, because we're using FFT code, so we don't want to do some Gibbs artifacts and other artifacts, so we need a lot of voxel by grain. Low texture intensity, because we don't want to do the effect of texture of alpha grain with macrozone or so other things, and periodic bulk for FFT computation. We want to generate a two-scale microstructure, alpha and beta, and don't forget the alpha grain, it's embedded in beta grain. So for that, for simulate something, this one of microstructure, we detect from the bulk, we detect the grain boundary. For that, we do identification. The process is we study this aggregate like images, and we find the grain boundary detection with a Python script. After that, we can control by using erosion and dilatation method like image processing. We can control the volumic fraction of beta. And in the white part, it's beta grain. We can affect the beta orientation, and the black part, the alpha orientation. We can do something like that. For the beta grain, we choose 001 orientation. It's a red one. And for the black part, it's a random alpha grain. We can do something like that. And in 3D, you can see the results. So now you need to study the effect of beta grain, the scale of beta grain, and another scale, it's that the scale of alpha grain. For that, we consider a spherical beta grain in the matrix. And the matrix behavior, it's for another beta grain. So we can generate different orientation. The blue, it's the beta grain 111 orientation. Red, it's 001 orientation. And green, it's 101 orientation. We have 6 different cases, and we generate another case. It's with a random beta grain outside the spherical beta grain. Like that, we have average volume measure outside the beta grain, spherical beta grain. So now we can detect all from the bulk, all alpha grain intercept the spherical beta grain, and we can generate our microstructure like that. You can see here you are outside a beta grain with 001 orientation, with alpha grain, random alpha grain, and under sphere we have beta grain, it's 111, it's blue, with random alpha grain. We can make a lot of simulation about that, and we can study the interaction of alpha grain, beta grain, and so on. So if I resume the generation, it's like that. We have bulk alpha grain generated by Dream 3D and detects the boundary grain boundary. After we affect 2 orientation, one for the center grain and another one for surrounding grain. The size of sphere, you have a ratio of 12. It's just choose like that from different case of real material. And we generate two type of bulk. One with alpha orientation is totally random, and another one, or we choose the burger orientation. It's the orientation of alpha grain depend of beta grain. So we have a lot of bulk to a lot of aggregate. It's 4 aggregate by different center grain, 3 center grain, because we have for its matrix, 4 matrix, different matrix for 001, 111, 101 and random, 3 center grain, 001, 111 and 101, and two different type of orientation of alpha grain. It's burger orientation and random alpha. And we study 3 different volume fraction. So we have 72 combination of polycrystalline. Now we want to study the effect of alpha grain. The first study it's in situ optical microscopy tensile test with NCORE, digital image correlation. We compute the effective shear strength map, and we connect that with crystallographic orientation. We can see here, show the strain localization is close to 001 orientation. So when you see the red one, you have a hotspot, red hotspot. It's close to, it's not really in the 001 grain, it's close to its border of 001 grain in different cases. Okay, so now we want to see if we can find the same type of property of effect in our simulation. So we use FFT-based computation with house code Foxtrot. It's classical, we resolve a classical problem. Our code, it's the first type of code on FFT from Moulinek and Suquet. So we choose this elastic constant for alpha and this elastic constant for beta and solve just in elastic case. We can see a substantial variation in stress magnitude. It's different for different case of center grain of matrix. You can see sometimes the high stress it's in the spherical beta grain and sometimes outside, and more contrast with Berger's orientation. Okay, so it's just visual. So when you plot the normal stress frequency, we can do simulation for just alpha grain, no beta grain. You have this histogram, and this you can see some kind of anisotropy, and another, because we have a lot of orientation, so it's some kind of effect of anisotropy here, and you have random beta orientation, a lot of random beta grain. So it's the anisotropy, it's higher. When you add for the same volume fraction of beta, when you add different case of orientation, you can see the anisotropy it's higher. So we can study here when the center grain it's 001, the alpha grain stress it's higher than beta grain. When the center grain it's 111, it's the inverse. and for 101 it's some almost same. So we can see the concentration of stress in different cases depending of orientation. For the same alpha grain, the concentration of stress is different depending of beta grain surrounding. So we have a substantial variation in stress magnitude, and anisotropy variation, it's alpha, it's less anisotrope to beta, less anisotrope to alpha plus beta. And stress redistribution between alpha and we have a stress redistribution between alpha and beta phases. So now we want to see the localization of hotspot. Remember here in this case the hotspot is like that. You can see it's close to 001 grain. So in our study you select the hotspot. So for the grain 111, the hotspot is close to the bonding of center grain, and for the 111, but it's inside central grain, close to the bonding, but inside. And for the 001 localization, it's outside, but close to center grain. And for the 101, I'm not sure here, but depending, sometimes it's inside, sometimes it's outside. The alpha grain with highest average stress magnitude along the longing direction for the random orientation outside center grain and inside center grain. Now that is just elastic model. So before to start the plastic models, we want to study the maximum resolved shear stress redistribution. So we project. It's just a projection of stress in different slip system. You can see here for the higher maximum shear stress value, it's for 001 orientation beta, for burgers or not, burger or random. And the second maximum shear stress value is for 101 for the random alpha, and 111 for burger orientation. The sequential slip activation predicted from beta orientation containing alpha is significantly modified with burger orientation. So now we study the influence of beta fraction, volume fraction. So here we can see at fixed orientation, if I fix orientation, the stress increase with volume fraction. So the normalized stress increase with volume fraction. This I don't say that, but it's a normalized stress just in alpha grain. So increase with volume fraction. Okay, it's almost the same orientation, same information in this graph and this graph. The effect of beta phase volume fraction decrease with beta phase stiffness. Okay, and you have more anisotropy. The effect increase with and the weaker effect in 111 grain probably stem from the lower stiffness. Okay. Now we want to study the effect of elastic constant. So we have a lot of elastic constant in literature. So we choose two elastic constant with different anisotropy ratio here. A lot of different, and from the same team, like that the identification method it's the same, I think. So when study that, we have stress magnitude in alpha phase are significant. It's very significantly influenced by the set of elastic constant, and the difference is due to the Zener ratio. So now I conclude. My conclusion is the stress redistribution was found very sensitive volume fraction. The orientation relationship between alpha and beta phase influence the mechanical field. It's obvious. Stress hotspots close to beta grain, like experimental data and simulation data, it's the same thing. Berger's orientation do not change the onset slip for beta 01, but change the resolve shear stress amplitude. We need to study that. And the crystal elastic constant, it's a real influence. So as a consequence, a new effort needed in this step. Future work, but it's already done. Morphology effect with different beta grain, EVP computation, and add lamella. So that it's work in progress, but the result seem good. Thank you.